the cloud. Okay, so everything is, so, all right, so this is the finals here. Oops, wait, I didn't want to do that either. Finals here, so there's two papers. All right, so there's two papers that are simulation papers, both of them. Hide this. There. So one's hard. This one's pretty hard. It's about Rouse. It's kind of about Rouse. It's about reptation, Rouse. And the other one is seemingly pretty easy, which every time I say something's easy, that means it's hard. But basically, this is pretty simple. Like he's just got, he makes spheres. It starts out as a word that I don't remember, like a something a hedron. Hexa something.
I think it says icosahedron.
Yeah.
Oh, really? All right.
Yeah.
As a title or something?
No.
Scroll up.
Section 2 is like the second one.
The numeric one, where it says two numeric and a little bit more, that third line is the second one.
Right. That's it. Icosahedron. So I think maybe 6 coordinate is useful. So it's got every point and it's got 6 arms coming off, makes kind of a hexagon. And then that can form like a buckyball kind of thing or something. Anyway, it makes something, but so all right. So both of these things, anyway, he looks at the collapse transition of that thing, which is kind of like what we did with coils. And then he uses the scaling theory for it, similar to the coil collapse, except in this state, he ends up with a self-avoiding walk, like a good solvent condition. And in this state, he's got a sphere. He starts with the icosahedron, and then, so the first step when you do this is you can make that on your computer. You can make an icosahedron somehow, like just write a program, somehow it'll do it. Or maybe there's one there. Then you have to get to the point where that thing's like a sphere, like a vesicle, like a surfactant that will make like little things like a micelle, but it's like not so you can make it into a sphere by taking that and kind of shaking it, right? So shaking it, you do a Monte Carlo routine to get this initial sphere thing. So you start with that, which you can construct easily, and then you want to have a random sphere thing. So he takes every atom and he does a Monte Carlo thing, which means like, I'm going to move it here, then calculate the energy for the whole thing. If the energy is dropped, I accept that. If the energy is higher, I roll the dice using the temperature as a weighting factor. So they're weighted dice. And then I say yes sometimes when it's a bad energy thing. So I can overcome energy barriers. So you just let the thing like shake for a while, and eventually it forms like a spherical bubble. Right. So anyway, so that's the initial thing. That's done. That's not done in lamps. So both of these things use lamps. That's what I was trying to get to. So the initial thing is Monte Carlo to get to a starting point where he has a sphere. Then he's going to use lamps, which is a molecular dynamics package that everybody uses. So the point of this, so several other papers of the semester, people used lamps. I think every simulation paper used lamps.
Lamps was the protein adjacent, or the protein model that also happens to work for polymers.
No, that was charms. So there's another, so all right, lamps generally is used with implicit solvent, meaning there is no solvent. So you say like you have your spheres, they have an interaction energy. That interaction energy is actually the interaction energy. So you just have one interaction energy, but it includes the solvent in it. It's bundled. That doesn't work if you have water, because water like approaches hydrophobic surfaces and orients in a certain way, and it changes the entropy, and the system doesn't really work with water. It works with an organic solvent that doesn't have kind of interaction between the things and the whatever it is you're modeling. Anyway, the lamps is much simpler, and it's going to work like every time, and the charms thing is going to be more difficult. So if you're doing bio stuff, you have no choice. Lamps can also do non-implicit solvent, but it's not really designed for that. It's designed for this simple toy molecule thing, but the predictive capability is like huge in it. So anyway, so I put in here that is not part of the homework. So we went through lamps in this thermal class, grad thermal class I teach. So there's all right, so this guy, let's see, this thing, sorry. This guy Brackley is at Edinburgh, Scotland. So Edinburgh's like historically I think it was Maxwell and a bunch of the other kind of thermo engine guys were there. So it got a name as like the top school in England, kind of. I mean, Scotland's separate from England. It's definitely the top school in Scotland. This may be like after Cambridge, Oxford, it's kind of like Edinburgh's the next one, you know, and it's also kind of like a Harvard. It's like the Harvard of Scotland, okay? You know, but Scotland's a small place in a sense, but anyway, so it is kind of a high level place. Then, so like anyway, so a lot of people have gone through Edinburgh, even though you mostly know it because of Harry Potter. Like that's kind of where Rowling sat in a coffee shop and wrote the books. Who's now like somehow politically incorrect or whatever. I still like the books, you know. So anyway, so this thing will take, if you want, if you have, so this will take you like a half a day. But after you do this, you will feel really comfortable with molecular dynamic simulations. So, but if that doesn't matter to you at all, then basically don't do this. But I'd suggest, so he wrote this for an undergrad course that he teaches. It's basically like, sure, it tells you how to download lamps, put it on your computer. You have to compile it, or you can use a non-compiled version for the first 5 steps. And the 6th step, you have to use a compiled version. So he says like before compiling, but he goes through step by step what to do. It's pretty cool. You end up with polymer chains with sticky beads on them, and then it will collapse down and make like a folded protein kind of thing. And all right, so using this code, almost exactly what's in this, like he published a Nature paper in 2000 something. Right, so this is Brackley. He's the first guy here. So he published this thing. This is exactly what the simulation will let you do. And but you can make movies and like watch the molecules move around. He probably has that as a supplemental in this thing. This isn't the homework, but basically I'm just saying there's 2 things with lamps. If you want to know kind of more about it, this is I think this is a pretty good thing because it's all spelled out exactly. It's step by step, just like that thing I gave you with machine learning. It's like the same thing. So anyway, we're not going to do that though. So anyway, that's there, that link. We did do it in, oh, this is an example of what you'll get out of it. Like, I forget what this is. This is, I think, branched polymers, binary mixture of star and branch comb polymers. And then they're going to phase separate, I guess, by the end. So basically something happens at the end. I guess nothing much happens. Anyway, that's an example of it. Right, so that said, so that has nothing to do with the homework except lamps, right? So anyway, so yeah, so typically, so you're going to use like a 612 potential. What is the guy's name?
Leonard Jones.
Leonard Jones, yeah, and that's the guy. He hyphenated his name with his wife's name. There's only one guy that invented that potential, but he hyphenated his wife's name with his name when he got married. It's pretty weird. Anyway, so should be a lesson to you all, you know, I guess. But anyway, so and this is a spring. So it's a spring. The energy in a spring is the square of the distance separating the things. So if you take the derivative of that, you get a spring constant times 2 times the distance. So K times X is a force. Derivative of the energy is a force. And then this is another torsional spring constant for something like a sheet. See, K is like the flexional spring constant for like a sheet kind of flexing like that, kappa. And then this thing is like I think this is the angle, or the normal vectors. So you have 2 dot product of the 2 vectors, like the angle of the flex that happens. And there's 2 vectors because it's like on an XY plane. And also this ends up being a square of kind of a distance. So you have this kind of format that when you have the energy, you have a spring constant, it's going to be the square of the thing. And that comes up later on when he does the energy ratio something that's in the homework. This is question 2. So this thing, so it's like the energy ratio is also the square. So this is just a spring constant thing. In other words, the energy for spring constant is going to be the distance squared. And so you take the derivative of that, you get the thing times a modulus times a spring constant. Right. So this is just a normal spring equation, except that he's talking about an energy ratio between stretching a film on a surface, the energy to stretch a film, and the energy to bend the film. So, and the thickness has to do with the bending, and the H, which is the amplitude of the vibration and the direction of the flexing. That's the distance that it bends the other way. So basically, that's just a spring constant equation. Right, so explain. So the origin of that is pretty simple. Even though you might look at it and say, like, what is that? Right, so anyway, so what else is in here? So is that business, and then so to get things moving. So he starts with the thing equilibrated into a sphere. And then he's going to put a random velocity, this VP, into each of the beads. So in these kind of coarse grain molecular dynamic simulations, you're always going to have a bead. Here's a bead at each of the corners, and then there's a spring connecting the beads. So everything's going to be a bead with 6 springs attached to it that form like an object, right? So you can construct that, and just lamps will take care of everything else, basically. And then he's going to let it just, all right, so so there's 2 ways to kind of change the energy of this thing. One is to change the temperature. There's probably more than 2 ways. Another way is to induce a velocity, initial velocity in each of the beads, a random direction initial velocity, VP. So he's going to plot everything against VP like this. So VP is kind of the energy. So it's the energy of the system. So if he has a fixed VP and random directions for all his beads, that's the energy of the system's 1/2 mv squared equals kT. So that's the temperature, right? So the temperature is the velocity in a system like this. They're linked together, right? So anyway, but he says that if he just changes the temperature, this doesn't work. He says that at the end. It's like you could wonder, like, why is he doing this weird? Because normally you just change the temperature, and then basically all the parameters are governed by the something over temperature. So temperature decides. He lists the parameters in here somewhere, but anyway, but basically he doesn't do it that way. He does it with this velocity. He doesn't explain exactly why temperature doesn't work. I think he says, like, I don't know why, but basically velocity does work. So when you let this thing have a random velocity, it collapses at a certain velocity. So it's almost like a critical velocity, except it isn't a delta function. It's this gradual thing. So it's a second order transition. It's not a first order. First order would be like, da, 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 you get to the critical velocity, boom, it goes. But here, second order, it's got this gradual thing. Right, so the slope changes, but it doesn't have a discrete kind of energy, a transition. Right, so that's kind of interesting, I guess. I mean, probably. So you remember with the coil collapse, with the chain collapse, it could be first order or second order, and that had something to do with the third virial coefficient, and the relationship between the second and third virial coefficients decided the order of the transition. He doesn't. So because he's doing molecular dynamics, he doesn't need thermodynamics. So he can just let it run, and it's like an experimental observation. He doesn't have to describe like what's going on exactly. So he doesn't. And anyway, this kind of transition doesn't exist for polymers. This would be like a transition from, say, like you had a straightened out rod, and then it went to like a expanded coil, right? So it's like a transition. It's not a transition to a collapse state. It's a transition to the random state. And the random state looks more crumpled than the non-random state. So anyway, people have theoretically postulated like what this random state of a sheet would be, and they did it in terms of take the sheet and then draw a line across the sheet. And if you're in the initial state, that line's a straight line. So the fractal dimension of that line is 1. Right. So this new scaling parameter is also 1 because it's 1 over the fractal dimension. Right. And then when he gets to this state, he says it goes to the fractal dimension would go to 1.25, from 1 to 1.25 for a line that's going along the surface of it. So it's going to be like a tortuous line instead of a straight line. That's going to have like a slightly higher dimension. So it's only slightly tortuous. So the new parameter is 1 over 5/4, 1.25 ends up being 0.8. Right, so 5/4 would be 8/10. So that way, so it's 0.8. So, and he sees that, like he gets that after he does whatever he's doing. So if he's got a slow velocity, he puts in, he gets some other number close to 1, it hasn't changed much, then all of a sudden it goes to 0.8 at the end. So it's nice, it fits with the theory, like his result matches up pretty well. He gets that. So how he gets that, because you have this structure, you can Fourier transform it and get the scattering pattern. And lamps will do this for you. So these are all like script entries into lamps. Like if you run that thing, you'll see that you can just do a script entry. Give me the Fourier transform of this. It spits out the structure factor. Then he says in versus the molecular weight. Then he says like he can calculate the size of the thing from he can calculate the rate of gyration of the spheres, and he says he's going to have the scaling relationship between Q and R to the nu. Nu would be like the scaling dimension. So to get these all to fit together, he finds a universal scaling dimension for each molecular weight that follows this thing. So he's going to find 0.8 by doing a Fourier transform of his object and then getting the scaling dimension by getting the curves to fall on top of each other. So so that's kind of interesting. It's kind of a weird thing because he already has the sheet. So all he would have to do is draw a line across the sheet and measure the fractal dimension of a line. Like that could be done in lamps too. He didn't do that. So I'm not sure why he went this route. It's kind of a involved route to get the answer that you could get just by, because he has, when you're done with this thing, like you'll have thousands of these little objects, and you can just get the average kind of distance of the line, average mass of the line, and then just say like, what's the dimension of it? But he didn't do that. So he also finds that so he has different molecular weight chains. He's got these different spring constants that he used. So this is just a stretching spring constant, and this is a bending spring constant. So he varies that all over the place. And he finds out that this parameter is like how expanded, like the volume final over the volume initial, which would be 1 initially, and then it drops when it collapses. That depends on, you can remove that by taking the, so if the velocity, anyway, this square root of the kappa makes sense because that would be this thing about square of the distance give you the energy. So you take the square root of the kappa to get something. Anyway, so he explains that in here, but the square root makes sense. The 1.25 doesn't make any sense, but nonetheless, you can reduce this by the spring constants and get a universal behavior out of it, out of the collapse, which is nice too. So it's a pretty nice paper. I mean, it's seemingly meaningless. In other words, there's some applications of this. I mean, one is like you have a virus, which is exactly this icoso deco, whatever. Like a virus is that with some feet on it. And the virus comes up to your cell. The feet have proteins that want to attach to your cell. The virus pokes through the cell membrane and injects RNA. And then you get a cold. Right. So the collapse of that capsid of the virus is exactly this process. So if you can kind of figure out what's going on with this, maybe you could say something about curing the common cold, for instance, So there are some applications to this lamp simulation, right? So it isn't just nothing. Also, vesicles fluctuate and things like that. So there's a lot of vesicles in your human body and also in soap and everything else. So any kind of biological or semi-biological soft matter thing's going to have these kind of shell things going on. That said, so this thing, I said kind of where that came from. VP is this initial velocity, random velocity puts on all the beads in the capsid thing. And then it's, so supposedly 1/2 mv squared would be KT. So VP is like the square root of temperature in a sense. So it relates to the energy of the shell in the second page, first column. So that's first page, second page, first column. So he gives all the equations here somewhere. K bending constant, and gives the units of them, which means that's what they're related to. So So, yeah, like for instance, the diffusion coefficient is if you have one of these beads and it moves one diameter of a bead away, that would be, in the time it takes to go from one bead to one diameter away is the relaxation time. And relaxation time's like 1 over the diffusion coefficient, like something like that. So basically everything's defined in terms of kind of a standard, that's standard lamps talk. Like that's just all standard stuff. Like when you do your thing, it's kind of the same definition. If you do the other thing, you'll see it's the same definitions that are used. So, and then, all right, so then he adds in this white Gaussian noise, right? So basically all these things are going to have some noise parameter, equation 2. So equation 2, so he's got this zeta t, which is usually called g of gt when we did it. I showed you something like that in class. So basically that's a random delta function that pops every now and then, and the magnitude of it has to do with the temperature. So that's kind of a kick. That's a Brownian motion, like the atoms are floating around and gas atoms hit them and it kicks them and makes them move a little bit. So the motion in a Brownian motion thing has some kind of a random gas atom hitting the thing and moving it. So this thing is the equivalent to allow you to have Brownian motion. You have to have some kick thing going on, like a random kick. That the Brownian motion is random. That introduces the randomness. So randomly fires a shot at the particle and makes it move, like jostle, and then it decays after that. So that's also kind of a common thing, I guess. Crumpling first or second, so second order, explain why. Can you come up with a simple explanation? All right, so I came up with a simple explanation. Like if you have, so if you have the beads and then you're going to introduce a velocity in a random direction. So if they move in, they're totally almost free to move in, right? But move out, then they have like a tent of bonds holding them where they are, right? So they can't move out because they have 6 springs keeping them from moving out. Moving in is like much easier, right? So that there's a difference in between moving out and moving in. And it's easier to move in than out. And that would lead you to just collapse. Like it would want to collapse because it's going to move in until the things like bump into each other or something. That's the excluded volume thing. So he says this is an excluded volume model. So excluded volume means when they come in, they hit each other and then they can't go any further. So it's not going to totally collapse because it has excluded volume, but it can't, it's much harder for it to expand than to collapse to a certain extent. So it's going to end up collapsing. That's my thing. So does it explain that thing? Does that explain for, you might have a different explanation for it, you know, but basically that's mine. And then do you explanation indicate first to second order transition? I don't know. And that's an open-ended question. Hard to tell. But anyway, I don't have an answer for that, but you can make something up or not. You have to answer something, but not, there isn't really a right answer. Why does reducing VP by the spring and torsional moduli result in universal behavior? So that's because, oh, I definitely knew that at some point. So that's this thing. So he gets universal behavior. So everything scales back. So everything depends on kappa to the 1/2 because it's a spring constant, and that's how velocity relates to the spring constant. And then the 1.25 doesn't make that much sense. But basically, VP is going to depend on the spring constant and the bending coefficient, the two of those. So that's kind of the answer, I guess, to that. It's just, I mean, it kind of has to depend on those. And then this is like, so he does Fourier transform. So he has the positions of the atoms. You can Fourier transform those positions into a structure factor. And then you can take that and plot it against Q. So your spatial dimensions turns into Q in the Fourier transform, and the position, the mass turns into the structure factor. So you have structure factor in Q. Then once he does that, he does some like crazy scaling of everything to get this new. So it's a little kind of, I'm not sure if he gets a scaling coefficient so he can match all the SFQs by changing by scaling it with this thing. So there are all different size spheres. So they would be, it would shift left and right. So you can shift it left and right using the size of the thing raised to some power. That power will be the fractal dimension if you figure it out. And then that's how he gets this number. I kind of told you that before, but maybe you might answer that more eloquently. But why do you think didn't use a simpler method like just drawing a line? There isn't an answer to that. Probably my hunch is it didn't work. So a lot of these things are like, if there's some question like that, it's because it didn't work. All right, so that's the easy paper. Any questions on that thing? Yeah.
I could see, why is it easier to move in again to crumple?
Because you got like a tent of springs. See, this is my idea, you know, it might not be valid, but basically the way I see it, you have an atom, you have a tent of springs that are pulling it back in. When it goes in, it's going to be much easier for it to come in because it can, everything can come in. Like it's not a network that's forced to be a sphere. When it comes in, it doesn't have that tension on it. It's going to pull in until it has excluded volume with the other one. So it's going to reach some kind of excluded volume crumpling. That's what I think. I mean, I think if you,
like it's more energetically favored to collapse instead of.
it's almost like you have a balloon. Say you could go inside the balloon and push out. It would be harder to push out in the balloon than to push in. That's what I'm saying. I mean, I guess you could probably make a formula for that, but that's the way I look at it. Like it kind of makes sense it would collapse and the velocity of the things to overcome this difference in energy to go in and out to some point, and that's why it transition. I guess that would be a gradual transition. So that's why it's gradual.
All those springs are net pointed in.
The springs are like pointed, so it's on the surface of the sphere. They're pointed away from the particle along this, like a tangent to the sphere. So when you try to pull it out, it's like all attached. You're trying to pull 6 springs for each particle as it goes out. And when it goes in, it's still stretching those springs, but the other ones are not torquing on it. They're going to be able to flop in kind of. It's hard to say that in terms of math, I guess, but you know, basically just from a physical model, like if you work with a balloon or something, maybe it would kind of work that way. But anything else in that thing?
I can't help to relate it to a previous paper, when you were talking about the temperature not working, but the velocity working.
Yeah,
Sorry, what was it? Was it because, for like thermal, it has to be like first order, and this is not like a first order system, or does that not really have anything to do with it?
doesn't sound like it has. That's not it. I don't think there's an answer to why the temperature, it could, you know, if you could frame that up, it might make sense, but I don't think that makes that much sense right now to me, you know, unless you framed it up somehow. But so temperature should, and the velocity should be the same thing. Like that, they aren't different, you know. So somehow they're different here. So why would they be different, you know? I don't know. I mean, it should be the same thing. So instead of, he sets the temperature, but then he sets this initial velocity of the particles and lets them do whatever they're going to do. It should be the same thing, except that the velocity is attached to the sphere, right? So, and the temperature isn't. So somehow the velocity linked to the sphere makes a difference here. Temperature isn't necessarily like linked to the sphere, it's applied to the sphere. So the velocity is part of the sphere, part of the object. So there might be something down that road. I don't really know the answer for that, except that this seemed to work pretty well. He's got a nice picture of what's going on. We'll get some answers from it.
I just remember, I think it was like homework 7, where it was like they had the T in the denominator, not like the numerator or whatever.
Yeah,
And that, for the excluded volume or something like that.
Yeah.
That would work as well. So I think that they had to switch it, and maybe he didn't do that because she was like, it didn't make sense to like, I don't know.
well, he can't get a collapse at all with temperature. It's not like it's an inverse dependence or something. He can't get any collapse with temperature, no matter what temperature he goes to. I think he says that somewhere in the paper. So that's pretty odd, you know. Especially where, you know, in the actual viral capsid, like you don't control the velocity of each of the beads in it. There are no beads in it, but basically you don't control the velocity of the components of it. You can easily control the temperature. So that part is a little disappointing. Like it means you can't really predict anything. So, except that you can manipulate the spring constant. I think that chemically, the virus probably manipulates the spring constant to set the same temperature. So maybe it is something predictive in it. Yeah, they're the same thing. It should be the same thing. 1/2 mv squared is kT. So they should be the same thing. But if you, all right, so there has to be some argument. I'm trying to find one. One is that the velocity temperature is like global, I guess, and then velocity is individual, and the individual beads are connected to the capsid thing. So somehow that makes a difference. Like some of the temperature is going to just move the capsids around the room. The velocities aren't going to do that because if they're random, they'll cancel each other. So there's no capsid translational velocity in this picture that he does. I don't know. There's probably some explanation for it, you know. It's got to do with maybe the connectedness of the beads. Anyway, so let me just get this other one that's much harder. Also a lamps thing. Anyway, this thing is talking about when you take a melt, the polymer melt, and then you stretch it, right? So when you stretch it first, so you're trying to see the entanglements of the chains. So when you first stretch it, this is kind of how when you do a simulation, how you find the entanglement. So you have the chain in a mess of spaghetti, and then you kind of swell it until you can start to see that the chains will straighten out between the entanglement sites. So the only way to see them, even in a simulation, is to do something to the simulated mess of molecules. So you have like 1,000 molecules in a box, and you expand the volume, then they'll stretch out until you have straight lines between the entanglement points. And then that's how you see the entanglements. Like then you can quantify. So you do simulation, you finish it, then you take that thing and swell it to find the entanglements. You can count the entanglements in the system. Then you can shrink it back if you want, right? Or you have the initial one anyway, because it's just a computer thing, right? So anyway, when we did, so we got this Rouse, the new Rouse, this one. So I think it's 28 or something, 28. Yeah, 28. So we got this thing. So this is a like a broad spectrum for polybutadiene, G prime, G double prime. So this part, the slopes of 2 and 1. So it's a log plot. Slope of 2 and 1 can directly come from Newtonian flow. And I did that in class, believe it or not, at some point, but it's in the notes. Right, then you get to the point where it's not this is really slow time. It flows like a Newtonian fluid. Then you reach the point where the entanglements come into play. Then it forms a network. So it's like a rubber at that point. So you have the storage modulus is going to be 1 over the molecular weight times kT divided by molecular weight, or molecular weight between entanglements, right? And then you get this behavior of the loss modulus. It can be predicted using relaxation stuff. And then finally, so you finally get to the tube, so that the entanglements are making a mesh. But if you get to smaller and higher frequency or smaller size, eventually you get to the point where you see the tube, right? And the tube is made up of entanglements, and the chain within the tube is totally free to move. It has no entanglements, so it follows Rouse behavior. And the Rouse prediction is this frequency to the 1/2. So you get to really high frequency, you can see the frequency of the 1/2 thing shows up. It's not that clear in this data, but in data from more like my cells, it's really clear, right? So it's basically model polymers will show this frequency of the 1/2 here, which is a signature of Rouse scaling, which is like the train thing, right? Within the tube. So that defines the tube here. This is the Rouse within the tube. And that's basically the reptation theory in a nutshell. It's going to be Rouse diffusion within the tube. So that's what they're The frequency of so it's the oscillatory shear measurement. That's the frequency. That's the frequency times the shift factor. So when this is 1, that's the when you reach the viscoelastic storage and loss. Yeah, G prime, G double prime. Yeah, and then so when this frequency matches the AT, you're at 1 here, and that's the viscoelastic relaxation time. So it scales everything to that being 1, where this tails over. That's where the that's when you go to lower frequencies, the longer times, then the entanglements can relax, and the whole thing's just a liquid, right? So and then above that, they're firm. So you're at shorter times, then it becomes a rubber, right? So anyway, so yeah, so that's the picture. So he wants to kind of look at these systems and find this Rouse behavior. So in time, their frequency, it's frequency of the 1/2. So in time is 1 over. So it's time to the minus 1/2. Then you can see that Rouse behavior from the LAMP simulation of change. So it's the same software package he's using, and the same thing as that thing you can run through if you want. So yeah, there's a lot of, so this is all about the tube. So oops, so I'll park that here. So basically the tube stuff is here. So you have, with the tube, you have primitive path. So you have the, if you take the chain, which is a squiggly thing, and then you find the entanglement points that are going to define the tube, then you can kind of find a path that the chain follows straight lines between entanglement points. So that's the primitive path. That's going to have a length. Here he calls it L, which is kind of confusing because L is usually the contour length, like the black line length, but L that he uses in here is the primitive path length, which is that thing. Right. So, and then he talks about, so if you swell the thing in 3D, you have all these entanglements. If you do this step strain, so extensional strain, so you're going to take like a rubber band, you're going to pull it, right? Just tension, like a tensile test. So normally you're talking about shear measurement. This is an extensional measurement, right? So basically, if you do that, only some of those entanglements are going to be effective, right? So he calls them kinks, and entanglements is the same thing, right? So there's effective kinks and ineffective kinks, and then the red ones are effective. So basically, so as you're watching time, so if you do that stretch and then you stop, and then the chains will slowly like escape from their entanglements. So these effective kinks, which you can measure by this. So in lamps, you can take your fluid and stretch it. You can do this measurement. So you can do basically anything in it. Anything you can think of has already been done, and it's already been coded. You just do a script and it does it. So you can take the fluid, pull it. You can look at how the molecules change, So it's pretty sweet. I mean, it's actually kind of fun, but it's a little bit of like doing scripting, like the other, kind of like the machine learning thing was, right? So anyway, so anyway, you do that, and then you can count how many of these effective entanglements remain. So he makes a distinction between effective and non-effective. All these little distinctions are like kind of people hang their names on it. Like they invented this idea of effective, non-effective. So he's kind of invented in this paper effective, non-effective. And he says it's the same thing as what someone else called something else. So basically, anyway, so he can count how many of those effective links there are after he stretches it as a function of time. And he finds out there's 3 decay features to this. One is this kind of slow decay. Then he gets the Rouse flow. So that's what he's kind of looking for. Then he gets this exponential thing at the tail end, right? So if you look back, like here, there's also some kind of exponential thing going on here. So it could be it's true what he's saying, or it could be just he needed it because his simulation showed that. Long times are going to be harder to measure. It's kind of hard to tell. Anyway, yeah.
What is he trying to show with like effective and ineffective kinks? Like, 'cause I feel like in one moment of time they could be effective, and then in the
Yeah.
next they couldn't.
They could be, no, in one direction, right? So he's pulling it in the X direction, but those kinks would only be effective in like Y and Z. So like only some, when you pull on it, some of them are not aligned right, that they're going to get tension on them when you pull it. in the only measurement you can really do is this uniaxial extensional flow measurement. I mean, the volumetric one doesn't really matter much. You're always doing kind of an extensional flow with entanglements.
So he's trying to show like which areas will cause the most like restriction of movement.
Well, no, the problem is like if you count all the entanglements, you're not going to get this 1/2 slope. So he has to find some way to get the 1/2 slope. So he does everything he could possibly do in lamps. Finally, he gets this idea like effective and non-effective, and bingo, he has the answer. So he's tried every other possible way to do it. And then he comes back and writes a paper and he says, obviously there's effective and ineffective entanglements, and only the effective ones are going to be effective. So I mean, after the fact, you get to that, right? It isn't like he walked into the room, set up this simulation, and he knew immediately some of these are effective, some aren't effective, you know? So, and other people have written papers about it and kind of indicated that too. So it isn't just his thing. But anyway, there's a bunch of terms here. So one is, so the process of these entanglements disappearing is this, well, the change in the contour length due to that is contour length fluctuation. And then the process of those disappearing is this constraint release. So you talk about the constraint release model. So he doesn't really have to do much math. He just plugs it all into lamps and lets lamps do the work, comes up with an answer, then fits the data, right? So it's not a theory paper, it's an experimental paper, but it's done with a lamp simulation, right? But he also does a neutron scattering measurement. So he does the same thing. He stretches the polymer, sticks it in a static neutron scattering beam, and all right, so he stretches the polymer, he freezes it somehow, stretched, and then freezes it at different times after stretching, kind of like what he did here. Then he takes the frozen sample and sticks in a neutron scattering beam while it's frozen. So he can watch in neutron scattering how the thing changes in shape. So he'll get these scattering patterns that are shown, I guess, in his supplemental thing. Here, let me find that. Supplemental. So I think he shows it in here. It's like it's a 2D pattern that shows, see, some orientation. So this sample's been frozen. He explains in here what he does. Make the melt, stretch it uniaxially, then freeze it somehow. Hold on, he says somewhere in here how he does it. Anyway, so he does that. And then supposedly you can keep it frozen. Let's see, I guess it's polystyrene, so it would be frozen at room temperature. So he's relying on the glass transition to hold it together. Anyway, so, and then because this neutron scattering measurement is going to take 2.5 hours. It's not something, then his time scale here is 10, whatever. He doesn't give units, but it's going to be like picoseconds, essentially, right? It's going to be really short in this computer simulation.
The constraint release, is that basically like he does the rapid stretch and then constraint release is just laying it back?
No. Constraint release. So you do the rapid stretch. So, and it's the entanglements are other chains that are transporting, they're reptating. So they can reptate out of there. So the reptation time is the time that the chain takes it's in a tube to get out of the tube. That's the reptation time for the chain, the relaxation time, reptation relaxation time. So basically, if you wait that length of time, the entanglement disappears because there's no chain there anymore. Of course, at the same time, other chains are like weaseling around the same thing. So everything's a bunch of worms moving around. So it's kind of saying, well, because that one disappeared doesn't mean another one doesn't show up.
So the constraint is getting out of the tube.
Yeah, no, the constraint is the tube disappears. Constraint is the tube, and the constraint release is the tube disappears, but the tube doesn't all disappear all at once, right? I mean, it's going to be, these entanglements are going to pop with time because it's a statistical situation. So you're going to have, so this is the time, right? So, oops, stop. Right, so this is the time that the number of effective kinks is dropping towards 0. Right, it starts out with 20 and it's going to end up with like almost 0 with time, right? So effective kinks mean, right, so the chains that weasel back in aren't going to be under that strain that you applied because they're just coming in by diffusion. So the initial ones, you pull it, they're tense. And then those weasel out of their tube. The new ones that come in aren't tense, so they don't count. So only the ones that count were the ones that are tense and remained, which is some, statistically there'll be some, but by Rouse transport within the tube, you get this T to the 1/2 thing. T to the minus 1/2, frequency to the 1/2. So he sees that. So that's good. I mean, that kind of tells him. Then he describes these other two regimes here. Let's see. This guy's not doing what I want now. That's not it. So he's got three regimes, that regime, the Rouse regime, and then this exponential regime that he vaguely describes. He describes the exponential thing. It's here too. So it's not just an exponential, it's like a scaled exponential. The exponential doesn't work. So he has to put in a beta that's smaller than 1. And he says some things about how that works. So this is a pretty involved paper, but it's good to kind of look at. It should be challenging to do this thing. One thing is weird. So he also gets from the scattering thing. So he does this, and then, so how are you going to analyze this? Well, the normal way to do it is with what's called Hermann's orientation function. You take the circular azimuthal average of the thing around a circle, and it has 2 peaks in it. You fit that with a cosine function, and you get a function that goes from 0 to 1 for the orientation. That's like a normal way to do it. An odd way to do it is to use spherical harmonics, which are something odd that's used in various places, I guess, but some people have used it to look, I guess, especially in China, maybe they've used it to look at, right, spherical harmonics are you break down that pattern into a sphere. So it's not a sphere, it's a circle, but somehow you say it's a sphere, maybe it's like Ewald sphere or something. Then you take the different harmonics, be like 1, 2. Now this 1, and this is harmonic 2, which looks a lot like the SP orbital, whatever. So it's got 2 lobes, but the one lobe is negative and the other lobe is positive. How you fit that into his thing, he doesn't say. But basically somehow he's going to use the first and the second spherical harmonics, and he's going to use all the others too to describe the shape of that pattern. He's going to use the second spherical harmonic, which is the 2-lobe thing. One of the lobes is negative, so he ends up with like S of Q, which is normally a positive value. Like this, the ordering of the thing would be, it's got to be a positive because it's squared. In other words, it's the amplitude squared, so it has to be positive. It can't be negative. Nonetheless, by this approach, he gets a negative structure factor, and it shows a negative peak to it, which is kind of odd too. I mean, you'd think that the peak would be, anyway, there's a negative peak. And then basically he's going to use that to analyze to get his number of from this curve, he can get the number in F, the number of a finely stretched change. So a fine stretching means you take the rubber and you pull it, and then the rubber chains align exactly the way the bulk does. A fine means the bulk and the molecular are the same. So, and that's true at large scales, right? But there's some scale where you go down in size where the chains can't really feel that stretching, so they're random coils. And the cutoff point between where the random coils and where they stretch finely is this molecular weight in a fine. All right, so he claims that he can measure that molecular weight in a fine from the cube position. It's like the distance of the chains, and assuming that they're Gaussian or something. They can get this in a fine from that. Then he has a theory where he can translate in a fine to the ZEE, which is the number of effective entanglements. So it kind of conceptually kind of could make sense. You could get the number of effective entanglements if you could get n affine, and conceptually you could get n affine from the shape of this second harmonic spherical analysis of the scattering. So everything seems to be okay. There's a lot of faith involved here that the guy actually knows what he's doing. But in the end, he gets T to the minus 1/2. So that's like bingo done, right? So, and it's coming from China. You always have to kind of wonder, but basically they get T to the minus 1/2. And all right, I should mention they're paid per publications in China, and the higher the ranking of the thing, they're paid more. So there's a monetary benefit to finding T to the minus 1/2 here. And in the 3 points that show it out of 6 or something. So, but he also sees like exactly the same exponential decay at the high end and kind of the same flat lower thing. So he has 3 regimes even in the neutron data. So it's interesting. I mean, it's a pretty good paper. I mean, you can always throw rocks at things, but it's pretty decent. And it's, I think, compared to other tube type papers, this is simple. So the papers tend to get really involved and really like nitpicky about certain aspects of it. So anyway, that's kind of where this is. So I thought it was a good one to look at. I actually like this paper better than the other paper, but I thought the other paper was kind of simple. So you kind of, this one's hard, that one's simple. Like give some hints, like tell you where to look for things. And then he also mentions neutron spin echo, which Nichols talked about. So, and he says like it can measure the tube. So I showed in class that you could get the tube diameter from the NSE measurements. But then he says, can't demonstrate the presence. He says it can be used to demonstrate the presence, but can't provide direct observation of entanglements. So that, and he doesn't explain exactly why, so I want you to explain why. I guess direct observation in the context of what he's doing here, like getting ZEE, I guess is what he means by that. So you can't get ZEE from all you can say is there is a tube. You can't say how many entanglements made the tube. Like you can say the tube, you can say how big the tube is, but you can't say how many entanglements made that tube. And then as a process of the decay of the thing, you can't say how do they relax? Like what is this time dependent function? Where's the Rouse behavior of it? Like the NSEE isn't going to give you exactly the Rouse thing. So I think that's kind of the answer to that. There could be a variety of answers. This is just read the thing. Shouldn't be too bad. I give you the slide numbers and the new Rouse slides to show that plot, and then like the square root dependence. And then he gives us kind of obscure description of that exponential decay at the end, page 3206. It may or may not make any sense. I think to me, it has the flavor of what I say here. Like he had something, yes, he sees the 1/2, then the thing takes a dive at the end. And it should just keep going Rouse, I guess, until you get to the end of time. Basically, you just Rouse. But then he says, so then he gets this problem that shows this exponential decay at the end when he gets to the high times. So he makes something up to explain it. I guess that's the way I saw it. But anyway, if he hadn't seen that, he would never predict that, put it that way. Like if he hadn't had a problem that you can't describe that. And then this is just about the neutron thing. I talked about that. What is SOQ? That's a harmonic. There's a link to that spherical harmonic thing. Just take a look at it. He's not the only one that's used spherical harmonic to talk about orientation. So, but basically it's a pretty odd thing to look at, especially when you get a negative structure factor that doesn't make any sense at all. But anyway, anything on this paper? It's a hard paper, but
And is it based on like chemistry, like the side groups, chemistry?
No, the lamps is just beads. It's just beads with springs. You can change the springs to match up with, compared to KT, the energy of a bond. So you can match up the parameters with some polymer, but in the end, it's just beads and springs.
Polystyrene, so they at least might have those bulky side groups.
Yeah, no, the last thing with the neutron scattering is polystyrene, yeah.
Okay.
But he's using that because it's a convenient glass transition. So he can lock it in and he doesn't have to keep his samples frozen. Like it'd be difficult to keep them in liquid nitrogen and then take them and put them into the beam in liquid nitrogen and make sure the temperature didn't change or something. And polystyrene's like got a really well-defined rheological signature. The curves are really clean. So, and you can get it monodisperse, things like that. So he's using that for those reasons, I think. It's just kind of a model system to use. It's cheap, you know. and get deuterated polystyrene. It's still more than cocaine, but it's like relatively cheap. But compared to synthesizing your own, put it this way, deuterated PDMS we got, it cost $100,000 for like 50 micrograms. So in deuterated polystyrene you get for cocaine price, whatever that is. You know, so, but when you handle it around, you don't want to spill it, you know, it's that kind of thing. But it isn't catastrophic if you do. But anyway, so that's it. Yes.